mode. Let's see here. Share screen. Okay, we're going to go over this again since I think maybe I can do the best job explaining this, and it's very, very confusing. Before we do that, though, I want to review what we did last week. Sam, can you see the latest slide online here?
I can. It's in the kind of presenter's view, but it's fine for me. Like it shows the next slide in your notes.
Yeah.
On the same page, but it's certainly acceptable.
Okay. I'll figure this thing out eventually. So most of last week we talked about strengthening mechanisms in metals and a little bit about composites. Does anyone want to spout one out just to show you we're paying attention? Someone name a strengthening mechanism in this field.
Hall pitch.
What? Transformation strengthening. Have another one. Grain boundary. So Hall pitch. Anyone else? Precipitation. Very good. There you go. Okay. So we talked about those different strengthening mechanisms, and in some cases we were able to make some estimates of how much strengthening you can get from those types of mechanisms. We talked about dislocations. We talked about dislocation theory, that metals deform by having dislocations that move and shear across lattice planes. And this key to strengthening a metal is pretty much to make it more difficult for those dislocations to move across the lattice. And that's kind of the fundamental thing. That's how you strengthen metals. You stop the dislocations from moving, or you make it require more energy to move them. Okay, and we talked about structure property performance relationships, and we talked about heat treating of steel, the solution treat, right? So you may go from body center, or you go from body center cubic to face center cubic, and then you can quench and take back down to martensite, which is body center tetragonal typically. Okay, it can be, I think, it can be HCP sometimes. Well, I think martensite can be. There's like two different types of martensite. One was BCC or BCT. I think there's another one too. I think it's BCC. Anyway, and then after that, because martensite is very brittle, you can temper the material. Okay, and that grows the martensite, coarsens it a little bit, so it's not quite as brittle. It makes it a little tougher, but lose a little bit of strength. Okay, and then we got to this guy here. Okay, so this was confusing as heck. I agree. Here's the problem. The fundamental problem. Computational materials engineering is very, I'll call it PC. You know something here, you know something here, you know something here, you know something here. You're supposed to know something here and here and here, and somehow those kind of come together to strengthen the material. It's not quite as fit for like writing an algorithm for like finite element analysis, right? It's just all these little different facts you have to kind of know and put together. So as a result, the stuff I'm showing you here about designing materials is also kind of PC. And there's a lot of information that maybe I forget to tell you. You can always ask, please ask if you don't understand something, maybe there's something I'm missing. And then you bring that all together and okay, well, this makes sense. I see how this is strengthened. So the first thing I was mentioning is precipitation hardening. Okay, that some steels can strengthen via precipitation hardening, like this alloy steel here. The other thing I mentioned is that there's a thermodynamic driving force that grows precipitates during tempering. Okay, the thermodynamic driving force is related to Gibbs free energy. If anyone here, probably the material science majors, you guys know what Gibbs free energy is. Okay, so who knows what Gibbs free energy is? Okay, so Gibbs free energy is related to the sort of energy it takes to form different phases, or the material that's released when a different phase forms. Chris, you actually named this dog after Gibbs. Kids might want to know that. So the higher a driving force, which again is related to like a drop in Gibbs free energy, the higher the driving force for the precipitation of some secondary precipitate or precipitate material, the more likely it is you're going to get a fine dispersion, a fine broad dispersion of lots of tiny little precipitates and all over the material. Okay, the lower driving force, the more chance that you're going to get big globs and not many of them. Okay, the way to increase strength, as we saw before, because we talked about the critical size of precipitates, the way to increase strength, not increase strength by the maximum amount, is to have that fine dispersion of lots of little particles. So you want to, when thinking about choosing an alloy, for example, choosing how much chromium or how much molybdenum or how much vanadium or nickel, when thinking about choosing those things, there is the possibility to do calculations that will tell you what's the free energy for this, for these precipitates for this alloy composition. Okay. So the other thing we talked about was coherent versus incoherent particles. Remember, we showed that curve that showed how strength increases as the precipitates are growing until a critical size where then it begins to drop. That critical size is typically associated with incoherency. So the precipitates, the atomic planes in the precipitate no longer line up with the atomic planes in the lattice of the material. Okay, the opposite of that is a coherent precipitate where the atomic planes in the precipitate line up with the planes in the material. Okay, the second one, the coherent precipitate, that's the one that produces higher strength. It's higher for a dislocation to sort of get by that little feature in the microstructure than it is if it's incoherent. Okay, so there's all these little pieces I'm kind of throwing at you that form the picture of this is how we strengthen the material. Okay, so incoherency, coherency, atomic planes. So incoherency, coherency. So atomic planes don't line up, atomic planes do line up. Okay, dislocation cut versus dislocation wraparound. Okay. Okay, driving force gives you lots of little small. High driving force, thermodynamic change in Gibbs free energy gives you lots of little precipitates. Okay, the opposite is low driving force gives you big globby things which don't do as good a job strengthening because they're not coherent anymore. Okay, here we have two graphs that show contour lines, constant contour lines of driving force for incoherent and coherent precipitates. This one is an M6 where the M is a metal C, and this is an M2C. You want these, you don't want those. Now, the contours here were calculated via computer using thermocouple. These constant Gibbs free energy, constant driving force lines. Okay, these contours were calculated with thermocouple. Now, this yellow line right here, this represents the stoichiometric ratio of these two alloy elements, molybdenum and chrome. Okay. Now, I want you to think of this in terms of a design space. And we're going to talk more later about design spaces and how that applies to geometry. This is a two-dimensional design space. You've got two variables, the amount of chrome and the amount of molybdenum. Okay. This yellow dashed line is the stoichiometric ratio between those two in the material. Compositions along this line were investigated by a graduate student at Northwestern. I think it was Gary Campbell, but I'm not 100% sure. And those materials were mixed, cast into little ingots, and then heat treated, and then hardness measurements were taken for those little ingots. Okay, so that part was experimental. So you can imagine a graduate student, poor little graduate student, mixing a bunch of little compositions along this line, and then making little billets, and then solution treating, quench, temper these little billets. Okay, and then doing hardness checks to see how hard they are. What this graduate student found out. Okay, well, before I go there, actually. So if you want to reduce the chance of getting these M6C carbides, you want to reduce the thermodynamic driving force to form those guys. So you would imagine that as you go this way, downhill, your chances of getting the M6C incoherent carbides decreases. So lots of chance of getting them here, not much chance over here. Make sense? Okay, conversely, this is the thermodynamic driving force contour plot for the M2C coherent carbides. As you go this way, you reduce the chance of getting them. As you go this way, you increase the chance of getting them, or the right shape and size. There? Does that make sense? Okay. So if you're on this line and you don't want, and you want to reduce the chance of getting these guys, you go along this line this direction. If you want to increase the chance of getting these guys, you go along that same line this direction. Right? Now, just because this line is stoichiometric doesn't mean that you can't get metastable materials that are off of that line. You can mix up billets that have a different composition outside that line, and it's metastable. It might stay there for a long time. It may stay there for not very long. In this case, it stays there. The material will stay that way for a long time. Okay, the graduate student who's working on this found that trying to go down this way, trying to go as far this way as possible, make sure you don't get the M6C carbides, found that when, I think it was a she, when she got to 15 kilojoules per mole, that the material had an intergranular corrosion problem. So you couldn't go to a composition that would bring you further down this line without running into this problem during heat treatment. That meant that this became the boundary. So you could only go as far to the left as 15 kilojoules per mole. So you would pick compositions in this design kit. So percentage chromium versus percentage molybdenum. You could only go so far until you ran into this intergranular corrosion problem. This is found experimentally. This wasn't necessarily found in thermochemistry. So you know that this then becomes the barrier. You can only go so far in this direction, and your barrier is now this 15 kilojoules per mole line. Now, I've copied that 15 kilojoules per mole line onto this graph. And here it is, right here, the green line. That's the border, that's the constraint, that's as far as you can go. That's a constraint to this optimization problem. Now, you want to maximize the driving force for the M2C carbide coherence. So that would be sort of a tangent between this green line and the blue line. That's why that's the composition. And that's the one that gives you the highest strength. Okay, does that make sense? Robin?
Saying the further away from the yellow line that you get, the less stable the material is?
No, I'm not saying that.
Okay.
I'm saying that because this curve kind of noses over, this 19 kind of noses over like this. Remember, you don't want to go too far this way, because then you're going to start throwing these guys. So it's like it's an optimization problem. You can't go this way to dramatically increase the driving force for the M2C carbides, because then you're run the chance of increasing this too. So effectively, you want to go as far as you can that way to avoid them. But how far can you go that way and maximize the driving force for the M2C carbides? And because this 19 kilojoule per mole line kind of bends over like this, the furthest you can go is the furthest point to the left, which is right here, where you can imagine a tangent at that point. That's just along this line, that's the furthest you can go to the left. See, you're trying, okay, does this make sense? This is a little, believe me, I had to read this about 15 times to understand it too. So if you feel like it's a little weird, that's okay.
So why wouldn't you take the composition that crosses the 19 contour line, but it's like still between the 15 and 16 contour line?
Because then you would go down, you would also go up in driving force for 60 carbon. I guess the message here is that the MC6 carbides are better at deteriorating strength than the M2C carbides are in increasing strength. Okay, make sense? Hope everyone online who's listening to this understood. Sam, how'd that go? That make sense?
I'm still turning my head a little bit, but I think I'm going to get there.
Okay, if you want to talk to me afterwards, please let me know.
Yes.
Okay. This is a similar alloy. This is AF1410. This is an alloy that was developed by the Air Force for aircraft landing gear. All right, and what this is pretty complicated. This is all figured out experimentally. All right, and what this shows is that as a function of tempering temperature, tempering time, the change in the precipitate population. The thing I want you to focus on here is this graph right here. Strength. So hardness is a good proxy for strength. Hardness tests give you a good idea what the strength of the material is, but they're really cheap and easy. Right? So doing tensile tests, we actually have to make a dog bone and pull on it, find an inch-on machine and calibrate it and make sure that you don't break the loading what do you call it, the loading stage. Load cell, thank you. That's all pain in the neck, right? It takes time. It's easy to screw up. You can twist the sample. I've done many of them and broken many of them and screwed up many. So but a hardness test is pretty easy. It's pretty hard to screw up. Not impossible, but pretty hard to screw up. Just you take your material, you stick it in your Rockwell hardness inventor, you pull the lever and boom, it goes and you get a hardness. It's real easy. So because of that, material scientists love to use hardness because it's just really easy to use. So if you look at this graph, these graphs, it shows how the precipitates are changing as a function of tempering time. Okay, how they're changing in terms of how big they are, so particle size, the aspect ratio. So these things are not always round. Precipitates oftentimes have an aspect ratio. They're not necessarily round. Sometimes they're oval shaped or they're rod shaped or they're needle shaped. All right. The number, how many of them are in there? You want a higher number, remember, because then it's a finer dispersion. Volume fraction, lattice parameter. Lattice parameter is important because it gives you some idea of coherency versus incoherency. Above the top line here is incoherent. Below the bottom line is coherent. And you can see the hardness goes up correspondingly with that coherency. And then this is the fraction of these various M2C carbides. So again, the M is a metal. It could be cobalt, could be moly, could be chrome, could be iron even. Okay. And this is the percentage of the available sites where you can have these precipitates in the material for these three different precipitates. And then and this is hardness, right? So this is a real sit down and look at it for a half an hour kind of thing. Okay, and I encourage you guys to do this when you have some free time. But just looking at this thing and understanding, there's a lot of information there, right? Understanding how does precipitate number, how does precipitate aspect ratio, how does the relative amount of composition of each of these, how do those things affect hardness? Through understanding, okay, I know that having a close to round aspect ratio of my precipitate down here, right, from 0. I know that gives me higher hardness. So now if you had a program like Thermocalc that can give you some idea of the aspect ratio of your precipitates as a function of composition and a function of, say, tempering temperature time, that becomes a very powerful tool in order to design the material so that it has the right precipitate morphology to give you an increase in strength, a maximum increase in strength. Okay. And here is here's some output from Thermocalc. And this does just that. It shows you the mean radius as a function of precipitate time. These are some random graphs chopped out of Thermocalc that show you what the software can do. And so things like the amount of precipitates, what's the number density, what is the distribution of the different sizes and aspect ratios. These are quantities you can get out of Thermocalc, which then help you design a material. Thermocalc can also help you get things like phase fraction. This is a nickel alloy, and this shows you various phases that can form in nickel as a function of temperature. And it's really interesting to look at these about which phases grow and which phases disappear as a function of temperature. This comes back to things like quenching, given enough time, any phase will disappear at room temperature, right? Or anything that was at high temperature will disappear at low temperature. But if you can quench, you sort of lock that in. You lock that in basically for your lifetime, and then you can use that. You can use that as a design parameter. So you can, if you wanted some phase like this red thing right here, you wanted to have that at room temperature, you can then quench and lock that sucker in there. Then you can use that for strengthening. Here is an example of a 4130 steel. So I think when I was a grad student, I worked on just a class project where we were trying to make castable 4130 steel. So silicon dramatically increases the fluidity of steel and aluminum, actually. So you can make it more cast. That's important. You've got some complicated mold geometry. You want to fill this thing without any porosity. If your material is thick and gooey, it's not going to fill the mold very well, right? So one way that metallurgists and foundry people have found to solve this problem is to add silicon. Silicon increases the fluidity of like I said, steel, aluminum. I don't know if it does it to nickel, but I know it does it to steel and aluminum. And the problem, however, is that as you put in silicon, you end up changing the austenizing temperature. So if you keep adding silicon in order to increase the fluidity of your 4130 material, 4130 chromoly steel, you keep adding silicon in order to increase the fluidity. And then you try to heat treat, you try to solution treat at the same temperature you always did, around 820 or 830 degrees Celsius. You would find that the material won't austenize. That's a problem, because then you can't get marmoset. So thermocalc, you can use a program like thermocalc to tell you how does the austenizing temperature change with the addition of silicon. So you've got silicon, you're adding silicon this way. I mean, this way in the whole, not this graphics carbon, but I mean the whole slide here. You know, this is 0.2% silicon, 1% silicon, 2% silicon, 3% silicon. And then you see that the austenizing temperature is going up. If you were designing the steel, or you were working with the foundry to cast a part made out of 4130, this information would be really useful, because then you can tell them, like, hey guys, you gotta solution treat at a higher temperature. Make sure you tell your heat treat shop. Okay, so we just discussed the processing to structure link in designing materials. This is, again, this is PC. This isn't like something that just sort of naturally flows easily, and there's the do step A, B, C, D, and everything comes out great. You can't just throw this in the computer yet and have it figure this stuff out. There's all these different little things that are out there. And when you hear about computational materials engineering, and it ends up meaning a lot of different things to a lot of different people, because there's so many different things that it means, and so many different calculation programs that go into, you know, calculate different parts of different types of microstructures. And I think that's kind of a problem for the material science community, quite honestly, because it means that, I don't know, it means it becomes really impossible, I think, to get funding or to teach people who aren't metallurgists or material scientists what ICME means, and why should I fund this when I don't understand what you're talking about. So it's not as easy as, well, we made our solar panel a lot more efficient, or we made our wind turbine more efficient. You know, we made the blades longer so it's more efficient. Everybody's happy. It's much more involved than that. Okay, so you might be saying to yourself, like, I don't really understand what this ICME thing is. I don't understand why there's all these little different pieces. And there's not that many sort of general themes that kind of tie everything together. So if you feel a little frustrated, just sort of go with it. It's not, you know, if and when you continue with materials education or work in materials, all these sort of different kind of facts and ideas and principles sort of come together in your head at one point, and you begin to get a deeper understanding of time. So this doesn't happen overnight to understand all these little different features of computational materials engineering. Okay. So now we're going to talk about the structure to property link. So you have these different structures in your material. How do you then go from these little different structures to predicting a strength? You know, you can look at a microstructure in a microscope or a scanning electron microscope, and you can sort of think about parameterizing the material. What's the grain size? What's the aspect ratio of the grains? How many precipitates are there? How big are they? What's their aspect ratio? I think the ultimate goal of computational materials engineering in filling in the structure to properties link is to be able to do that, to be able to take those parameters that describe a microstructure and then say, oh, I think the strength is going to be this. If I add a little bit of silicon, or if I add a little bit of chromium, and the microstructure does this, oh, I know the strength is going to increase to that. I think that's the ultimate goal of computational materials engineering in the structure to properties link. Now, having said that, I'll say that that link has not really been filled in, I think, as well as the processing to structure link. You know, I talked before about Kaufman and Cohen here at MIT working on computational programs for calculating out phase diagrams. And with Professor Eager always tell me Wagner was a visiting scientist from Germany who taught Kaufman and Cohen about how to calculate phase diagrams using Gibbs Free Energy, for example. There's been a lot, I think the community has been working on that link a lot longer than the other, than the structured property. So having said that, here are some examples of places where we have been successful at this. Composite materials, so carbon fiber, epoxy, or other composites, maybe like an aluminum with aluminum oxide fiber. There's the rule of mixtures. It says that the strength of the different phases times their relative aspect or relative volume fraction, through adding those products together, you can predict the strength of a composite material. And this works sometimes. It's not perfect. When you have really straight fibers in your composite, it works pretty good. When you see, like, this classic woven carbon fiber that you see everywhere, it doesn't work quite as well for that, because the carbon fibers actually strain the material, actually kind of straighten out. So that's not really taken into account with this rule of mixtures equation. This project right here, actually, this is a project I actually initiated at Chrysler when I was there. This is a brake caliper for a car. And we made these aluminum calipers where we reinforced parts of the caliper with Nextel fibers. So Nextel is a aluminum oxide fiber made by 3M. And we were able to dramatically reduce weight without losing stiffness compared to a steel caliper, and without dramatically increasing the space you need in order to package this thing. In this case, locally, just where we had the reinforcements, which was in the bridge area, kind of in here. The disc of your disc brake goes in here. There's pads, it squeezes together. Anyway, you don't need to know too much about this, but just understand it's selectively reinforced. In this case, the rule of mixtures actually worked pretty good because the fibers were really straight. That's one example. Here is another example, which I basically just told you about, which is going from driving force for precipitation to hardness. Here's a graph, also came out of Northwestern University, of hardness versus driving force for M2C carbides for this multi-component alloy steel here. And you can see, like, as you increase the driving force by tweaking the composition, the hardness pretty reliably goes linearly along this line. So hardness increases linearly with driving force for the M2C carbides. A good example. We talked about Hall Petch strengthening. Tyler, you mentioned it, right? Hall Petch strengthening says that the strength goes inversely to the square root of the grain size. And we talked, I think, last lecture about Chris Shue's company, Extalic, and the other one, Veloxant, where they use this effect of shrinking the grains to increase strength and hardness very, very effectively, very reliably, very repeatedly. We talked about how these things change with time too, because the surface energy associated with having so many grain boundaries. These equations here I presented to you before on the previous slides, I think last lecture. So these are models that predict the increase in shear strength for Hall Petch strengthening, for work hardening, for precipitation strengthening. Okay, we talked a lot about that, right? And then in solid solution strengthening. It turns out that these things are additive. The increase in strength of the material is directly related to the sum of the strengthening from all these different factors. This is a model right here. This is a model that's really simple, right? It's just all these different models added up together. This is a model for the strength you can get if you can get all these different mechanisms to work at once. This is a really simple version of it. Okay. It doesn't work perfectly. It's a good, reasonable first approximation. There are a lot of efforts by the military mainly to improve upon these models. And there are, I think, there must be some of this work going on here at MIT. I know there's some going on at Northwestern. But the military has expanded the complexity of these models. I can't tell you all this stuff. I don't understand it myself. It'll probably take me a year to figure it out. But all these, there's a lot going on here. There's a lot more besides these simple equations I've showed you that are better at calculating or predicting the increase in strength from enacting all those different strengthening mechanisms. Any questions on that? So again, this is predictive modeling of the structure of the property zone. These are different models. I just showed you some different models that you can use in order to predict strength based on just looking at the microstructure. Just collecting parameters on the microstructure from, looking at a microscope and a micrograph or a scanning electron microscope or transmission electron microscope. Now we're going to talk about the other quantity, stiffness to density. All right, so we said this before, that one of the key materials properties that is important or predictive of how much weight you can take out of a structure is the stiffness to density ratio. So in your undergraduate materials courses, I think you've all had undergraduate materials courses, right? Your undergraduate materials courses, they should have taught you that the stiffness of steel and its alloys or aluminum and its alloys is all basically the same, right? So for steel, the Young's modulus of a low alloy HSLA, high strength low alloy steel, it's probably about 205 gigapascals, right? I'm shaking your head. What's your name again? Ryan, okay. The stiffness of a stainless steel is about 210, somewhere between 205 and 210. The stiffness, the Young's modulus of a low carbon steel is about 200. Okay, so you're only going from 200 to 210. It's a small increase in stiffness. It's basically meaningless. Okay. So aluminum is the same way. 6,000 series aluminum, 7,000 series aluminum, 2,000 series aluminum. They all have about the same stiffness within a very small percentage. And for the most part, this holds true. But this kind of leaves the materials community in a problem. If we need a material that has this increase in stiffness per density, if that's what's going to allow us to make a lighter structure, how do we do that? We can't just use better steel. We can't just use better aluminum. Like, what do we do? Okay, I think this is kind of a discussion I had with Professor Shu last week. This seems to be an area that's kind of like people are just beginning to look at and say, okay, how do we really improve stiffness of a material? Okay. Okay, the fundamental paradigm of material science in systematic form, the Olsen diagram. How do we fill in this link? So does anybody remember this part about how Young's modulus is calculated, or what factors in a material affect Young's modulus? Remember this about the potential well? No? Okay. Actually, before we go to this, I want to say one thing here again. If you're designing a structure for something, for a lot of things like cars especially, probably less so in airplanes, but definitely for cars, a lot of times a given part that's being designed, the final dimensions that part gets to is controlled by stiffness and not strength. So you figure if you have a little bar and it's in bending, okay, and you have some strength requirement, okay, which by the way is related to fatigue. You have some strength requirement. This thing has to be able to support an elephant. Okay, and then you have another stiffness requirement. It has to be able to support an elephant, and when the elephant's sitting on the end of the beam, it can't shake it more than 20 hertz if the elephant wags its trunk. Okay, so what you do is you start sizing this beam that's in cantilever. Okay, you start sizing it. Bigger to get to your load. You reach some point where it's thick enough where it can support your elephant. And then you find out that its natural frequency is too low. It's not meeting that design requirement. So then you start going a little bit further, until finally you get to the point where the beam is stiff enough so that when the elephant wags his trunk, he doesn't shake it more than 20 hertz. All right, does this make sense? The point I'm showing you is that when you're designing a part, when you're dimensioning the thickness of the part, or the width of a part, the dimensions of a part, oftentimes in the design, you will meet your strength requirements before you meet your stiffness requirements. If it were the other way around, it would be easy to say, okay, if you meet your stiffness requirements but not your strength requirements, then it's very easy to say, well, let's just substitute a higher strength steel, or let's heat treat it differently. Let's use our computational materials engineering design a steel that's stronger so that it can meet our strength requirements because we've already met our stiffness requirements. But oftentimes in a real design, it really ends up being stiffness driven. So you find that how do you get to that stiffness? You don't have the tool just to say, okay, well, we'll use stainless steel. That'll make it stiffer. That doesn't really work. because this stainless steel is the same stiffness as the low carbon steel. By the way, you'll find in industry when you go out there, not a lot of engineers know this, that you can't really tweak stiffness. So what is stiffness? In your, I don't know, in your freshman chemistry class or one of your physics classes, you probably maybe talk a little bit about potential of moving two atoms together. You've got two atoms in an infinite vacuum and you move them together very slowly. And there's an attractive force, right? There's an attractive force that's pulling those two atoms together. But then when they get too close, the electrons get angry with each other and then they try to repel each other. So there's these two counteracting forces, repulsion and attraction. There comes to be some point where the potential goes to zero and those things find their equilibrium distance apart from one another. Okay? If you take the derivative of potential, you get force. Okay? The amount of force that it takes to pull those atoms apart or push them together is related to the Young's modulus, the stiffness of the material. The slope of this line is closely related to the Young's modulus. Okay? So this gives us hope as material scientists that maybe we can design materials that have higher stiffness. So if you take an iron atom, you take a silicon atom. Let me switch that. If you take an iron atom, you take another iron atom, you put them together, and you start drawing all this stuff out, you get one slope. If you take an iron atom and a silicon atom, and you do the same thing, you start bringing them together, you find out that, and you do the same thing here, you find out that this slope is actually steeper. So, and then even within silicon, like silicons form these covalent bonds, right? Those covalent bonds are much stiffer than the metallic bonds. It takes more force to pull apart a covalent bond than it does to pull apart a metallic bond. So, like I said, this gives us hope. Aluminum lithium. So, in the I think in the late 1980s or the mid 1980s, there was a graduate student here named Enrique Lavernia who was studying aluminum lithium, and he studied it well after he became a professor too. Aluminum lithium is an interesting material. So this is primary aluminum. You put a little bit of lithium in, and you can get an increase in stiffness. You can get for every 1% of lithium you put in, you can get a 3% increase in Young's modulus. Okay. So this is an example. You've got a lithium atom, you've got an aluminum atom, you've got a lithium atom. You start putting together, that potential well changes shape, and it makes the material just a little bit stiffer. As you put a lithium in, you also decrease the density of the material. So that quotient of stiffness, Young's modulus, and density, the bottom one goes down, the top one goes up, and you have like 5 to 10% increase in that ratio. So aluminum lithium was at the time back then in the 80s, was a very promising material because it hadn't commercialized this. But it did get commercialized, and I think it's someone correct me if I'm wrong here. Sam probably knows this. I think it's the 8000 series, the 9000 series aluminums now that have lithium in them, and these are very expensive. And there's probably what's Sam?
I was going to say, I think it's the 8000 series.
8000 series. Like one of them is scandium and one of them is lithium. But there's a similar effect with scandium. Did you have a question? Okay. So aluminum lithium is a very interesting material for increasing the stiffness to density ratio of the material. This is currently used in, I don't know, at least military aircraft, I'm sure. I don't know where else it's used, but energy, neat stuff. Okay. Silicon steel. So when you start putting a lot of silicon in steel, the stiffness goes up. It goes up anisotropically sometimes, meaning that if you're making a sheet of high silicon steel in one direction relative, so okay, you start with some big billet of steel, you heat it up, you put it through rollers, and then you thin it down successively. You heat it up, you thin it down, heat it up, you thin it down. It goes through several steps. That's how you go from a big billet to a sheet of this steel. This high silicon steel has a significantly higher stiffness 55 degrees, I happen to know this because I looked it up, 55 degrees to the rolling direction. Okay, and that could be useful, right? High silicon steels are used for electrical applications. So you guys ever take apart an electric motor and they have all those little plates of steel that are bonded together? Anyone ever done that? No one's taken apart an electric motor and seen the little laminates? Okay, if you took an electric motor, like the electric motor that's used on this this window covering here, or the thing that pulls the projector background up. If you took that little motor apart, you find that there's little steel laminates in there. So the little pieces of steel that are cut with a die, so they all have the exact same shape. And then they somehow either bond those together or they rivet them together. This is very effective at focusing magnetic flux, which then makes your electric motor more efficient. Guys like Elon Musk and Rivian and all these electric car companies, they know a lot about this. This is a hot topic. How do you get the best? How can you best focus your magnetic flux in an electric motor or a generator so that you get the highest efficiency of an electric motor or an electric generator? So like a wind turbine. Wind turbine's an electric generator, but it's similar technology as a motor. It's kind of opposite. But anyway, I'm stepping aside now. So the problem with silicon, though, if you add silicon, you make it more difficult for the material to be austenized, as we showed in the previous slide, right? It's harder to austenize. So if you can't austenize, you can't quench get martensite. So one thing we have to know, for example, is that nickel will decrease the temperature for austenizing. And this is just an output from Thermocop that shows that as you add nickel to this high silicon steel, they call this the gamma loop or the austenite loop. It moves, it elongates. So this is just showing that if you wanted to make this material and you wanted to strengthen it, you could, and you wanted to stiffen it, but you would lose strength because you couldn't austenitize and then make it into martensite. You could get that capability back by adding nickel. How much would you have to add? That's what Thermocop is good for.
Did they only get less stiff? Because it's kind of out some of the silicon?
I don't know yet, but that is the key question. That is the key question. What does it do? Okay, I was going to put this in here, but I didn't. I'll just tell you this. I should have put this in. I wasn't sure if we get this far today, but an interesting project I've seen is with a material called iron titanate. So iron titanate is basically fairly useless ceramic material. Okay, but it has an interesting property in that if you have a single crystal of the material and you're able to suspend it freely in a liquid or somehow air or something, and then you stick that particle in a magnetic field, the B axis, the B crystallographic axis, will actually align with the magnetic flux direction. Okay, so you have this little crystal of iron titanate. It has different Young's modulus, different stiffness constants in the three directions, three crystallographic directions. It's a cubic material. Okay, and if you have a little particle, you can align that particle in the magnetic field. That now means that you have stiffness that's different in three directions too. If you can measure the stiffness of that little crystal, you have different stiffnesses in each of the three directions, right? Because it's aligned. If you take gazillions of those little particles, you suspend them freely in a liquid, and you stick that in the magnetic field, all those little particles are going to line up with their B axis to face in the same direction. You can then center that material. You now have a material that has different elastic constants in each of the directions. It turns out some of those are higher, some of those are lower than the average. But there's an example of where you could potentially engineer a material for high stiffness by using it in only one direction, the alignment direction. Okay, should have put in a slide for that. How do you predict the structure to property link when designing for stiffness? Composite materials, it's a good example. Okay. The law of mixtures applies here as well. It doesn't just work with strength and density and thermal expansion. It also works with Young's modulus. So the stiffness that you can get out of carbon fiber epoxy is really quite remarkable for the density. And that's why it makes good structures for things like bicycles and racing cars and airplanes and so forth. Okay, here is a program that maybe you'll get a chance to use one day. This is called OOF. It's like Object-Oriented Finite Element Analysis. This was developed at the National Institute of Standards and Technology by Edwin Fuller and his team, and Craig Carter, I think, was involved with this too. Craig Carter is a professor in the math sci department here. Does anyone know him? Craig Carter, he's not your advisor, is he?
No.
Okay,
but it's like a competition on there.
okay. I should go say hi. So OOF is a neat program. What this program allows you to do is it allows you to take a microstructure that maybe you got from a scanning electron microscope, or maybe you got from an optical microscope, or maybe a transmission electron microscope. It allows you to take that microstructure, you scan that microstructure, and then you can apply elements. You can discretize the microstructure. It's pretty cool. You can assign elements to you can break each of the grains or precipitates or whatever phases in there. You can break that up into little elements, and then you can assign mechanical properties to each of those little elements, dependent on whether it's, what the phase is, right? So precipitate might have a different phase, might have a different stiffness than the rest of the material, or one phase might have a different stiffness, whatever it might be. Maybe it's an alley, you've got all kinds of weird stuff, and I don't know. But so you can assign properties to each little element for each little phase, and then OOF will combine all that together and tell you basically what the far field stiffness is. So this is another way. This is one way you could predict the stiffness or the structure processing rate. Okay, by using OOF. It's interesting. You can take this material, you can sort of parameterize it with finite element analysis in a computer, and then it'll tell you probably what the far field stiffness or thermal expansion or different properties like that are going to be. Okay, pretty neat stuff. You can actually download this. This is available on NIST website. I think it runs on Python now. Here's an interesting picture that I lifted from Greg Olson again. This is the different length scales and how they're modeled. What tools do you use to model these different length scales and materials with, going from structure to properties? And then what are the tools that you use that give you the data that you would use as an input for these models? And then shows, so the tools that you would use go up the left side, and then the models that calculate out the properties are on the right side. Okay, the Olson diagram. So we're running out of time here. This is a real world Olson diagram. This isn't just the kind of graphic I showed you, the sort of abstract version of this. Is a real diagram for a high strength steel. And on the right here, or on the left here, are the different processes: refining, taking oxygen out of steel, hot working it, solution treating, tempering, should be pointing here too. And then the different microstructures that you can have within a steel. There's the matrix material that can be like a martensite, it could be an FCC, austenite, it could be ferrite, BCC. The strengthening dispersion, these different precipitates that you can get in steel. Niobium is an interesting one. Niobium is a very effective strengthener for steel. Does anyone know why? There's two reasons actually. Anyone know why? Niobium is a very potent grain refiner. So it's able, through thermodynamics, it's able to shrink the size of grains down to increase the strength using Hall Petch. This is, I can tell you, like in the wind turbine industry, a lot of these wind turbines that are out to sea, like in the North Atlantic or something like that, or the Baltic Sea, north of Europe, and between like mainland Europe and Sweden and so forth. There's a lot of wind turbines in those areas, and it gets to be really low temperatures. And one way they can strengthen these materials, that they actually do strengthen these materials, is by specifying a lot of niobium in there. Not a lot, it's like only like a fraction of a percent, but it's a weight percent, but it's enough to refine the microstructure enough that it can get an increase in strength. The various codes that are used in the wind turbine industry, like there's one called Germanischer Lloyd, kind of a primary specification for lots of things having to do with wind turbines. One of them is steel composition. They specifically spec steels for these such of applications, like offshore wind turbines that have niobium content in them. niobium is able to strengthen steel not only by keeping the grain small, but also by forming very fine precipitates. Austenite dispersion. So when you solution treat a steel and then you quench it and it forms the martensite, not all of it transforms to martensite sometimes. Sometimes you can engineer the material to transform to some percentage of austenite, some what's called retained austenite in the material. And austenite is very interesting because if somehow you give it a little bit of stress, like a little crack tip was headed into like a little grain of austenite, it'll actually transform to martensite just from the energy associated with the stress. That change to martensite has a volume change associated with it. That volume change can actually increase the toughness of the material through what's called transformation toughening. You effectively apply a compressive load at the crack tip when you transform from austenite to martensite. These different structures are known to cause these different properties, right? To relate to these different properties, to result in these different properties. And anyway, these are fun to look at. I've stared at these things for hours many times, just understanding these various different links and the links between the processes give you these structures and these structures give you these properties. And the links of all these things go together. And these following these little squiggly lines around. Okay, last but not least, here is this is Professor Greg Olson. He is now a professor in this department at MIT. Previous to like 2 years ago, he was at Northwestern. And he founded a company called Questech, which has become the premier company for materials by design for computational materials engineering. They actually worked on the watch. You guys have an Apple Watch? Tyler, you got one? Is the aluminum or stainless steel? That aluminum was developed by Questech. So high strength, high corrosion resistance. Greg Olson is a member of the National Academy of Engineering. He's an ASM gold medal winner. He went to school here in the 60s. And I know him personally. He's crazy smart. He's hard to talk to because he's so smart. I mean that in a complimentary way. He has great taste in cars as well. So this is his Lotus Elise that he bought, I think, when he sold Questech. He also has a couple other sports cars. I think he used to race, but anyway. Okay, so he's got a Lotus Elan in. And anyway, real interesting person. If you get a chance to meet him, he's not going to be here till the spring, I think. But if you get a chance to meet him, I highly recommend you go say hi. Any questions, guys? No? Okay. If you have any questions, feel free to come by my office. I'm at 4-142. So basically across the hall and a little bit that way. Or send me an email or Zoom or whatever. Okay.
Thank you.
Thank you. Sam, any questions?
Not today. Let me digest this a little bit and I'll see if I can email you something.
Okay, great. Looking forward to it. Cheers.
Take care. Bye.
So you said that.
Yeah.
When you were talking about the beacon change from your austenite